Okay, so these are ions. Okay, how did these ones on, most of them are on the left, how did these ones on the left form? Just give me a simplistic, how did they, how did the fluorine get its -1 charge? Gained 1 electron. Okay? We kind of know a little bit about positions. Okay, now these other ones that have 2 elements in there, like SO4, it is a -2. So overall, that had sulfur and the 4 oxygen had so many electrons. And so how did it become a -2? So how did SO4, the oxygen means we got 4 oxygens and 1 sulfur. Okay, originally that had 32 originally that had 30 electrons. Okay, how many electrons does SO4 have now? It has 32. Because it brought in 2. Okay, so look at the positive. Here's aluminum. What did it have to do to get its charge? It lost 3. Magnesium lost 2. We better put some in here that lost 1. So we'll just do, let's do potassium. Okay, so let's just take a couple and match them up. So the positives can match up with the negatives. So let's go ahead and just do a couple where we're just matching them up. All right. So Eric, give me 2 we want to match up. Positive and negative. Give me a positive that you want. Just give me 1 positive. Okay, so we take aluminum. Aluminum is a +3. Okay, so aluminum is a +3. What do you want to match it up with? Just give me one of these you want to match it up with.
PO4.
Okay, so PO4. Okay. So PO4. How many of each of those do you need in which to get a charge of 0? So how many ALs and PO4s do we need of each to get a charge of 0? 1 of each, right? So our formula within would be AlPO4. Is there any subscripts I need with that? So if I have 1 of both of these, they already equal out when we combine them together. The charge is going to be 0 once we put them together, right? Okay. So that's AlPO4. All right, let's do another one. Kobe, give me 2 you want to put together.
Magnesium.
Okay, so we're going to take magnesium. And one other one. Which one?
PO4.
Okay, PO4. So he's going to do a tough one. So right now, if we would put these 2 together, hook them together to form a bond, what's the net charge? -1, right? Well, that's not going to get us neutral, and we want to get neutral. So we got -1, so what do we need to do to bring into this combination? Yep.
We need 3 magnesium and 2
Yep. eventually we need that, and that's good. And I'm starting off slow just to kind of show you that. But she already knows the combination, what it's supposed to be. So we're going to bring in another magnesium. We're going to act like you guys have not done anything with this. So we bring in another magnesium and we hook it in. So they're all hooked together. So now we've got, what's the net charge? Positive 1, right? So then we've got to bring in another PO4. And that's a minus 3. And then we count up all our charges and we realize that we have a minus 2, right? So then we bring in a third magnesium and we see. So we're always working to try to bring in combination of the plus and minus charges so that they equal out to 0. And so when we do that and we get them all linked together, there's our combination we need. And the combination we need is Mg, we need 3 of these. And for the phosphate, we need 2, right? Okay, so that combination, anytime you've got a plus 2 and a minus 3, you'll have to find a common charge, overall charge you can get both charges to. And so you just work through that and realize you need 2 minus 3s. And you need 3 plus 2s so that the charge is going to be 0. So you need 3, 2 plus 2s, and so that works for all of these, okay? All right, we're going to go back to this. Okay, before we go back to that, let's name this. So all we do when we name is, if it's a polyatomic ion, like the PO4. All we're going to do is look on our polyatomic ion sheet. So how do you know it's a polyatomic ion? Is because if you have 2 symbols put together and you got a subscript that goes with those 2 symbols, one or both, then you look off your polyatomic ion sheet, this one. And you find it, and what is the name of PO4? Phosphate. So phosphates is a common because it's phosphates are found in fertilizer, and so sometimes if you get too much fertilizer and it drains off, you get a bunch of these phosphates. It can affect, ponds and those type of things if there's too much phosphates. But that's another subject to come up later on. And then in front you put aluminum. So that's aluminum phosphate. Okay, and that would be the name. So this is called the chemical formula. Okay, and then this is the name of the chemical formula. Okay, some of you guys aren't writing this down, and that's fine. We're just putting our thoughts up there and that. So that would be how it would go together. It would be AlPO4, and that's the name of it. Let's go to our next one here. So this is what would be the name of this one? Magnesium phosphate. Okay, so we got that phosphate in there. Let's pick another couple on here. Let's make them 2 monoatomic ions. So Madison, why don't you pick 2 monoatomic ions? Mono meaning that there's only one symbol involved.
Potassium and chlorine.
So potassium and chlorine, this K and Cl. Well, we already know that they equal out, and so it's going to be just KCl that we'll have. So we just have KCl. So that would be KCl, one of each. And how would you name that? So you name the potassium. Then if you notice, the chlorine's not a polyatomic ion, and it's on the periodic table. So it has to be in an ion form. If the ion form always has endings of ides when you differentiate it from a regular chlorine atom. So this chlorine here is called chloride. Okay? And this chlorine is called chlorine. So this one's neutral. It's called whatever it is on the periodic table. This one has a charge, so we have to differentiate between the charges of our monoatomic ions. And it has to be just the anions. So this is an anion. Okay, and this is this here is a cation. So we have a cation and an anion together. And so they always end in ides. So all our monoatomic anions end in ides. Okay, one last one. All right, so we're going to take these two irons down here. Right, and we're going to match it up with the fluorine. So we're going to take those two, match it up with the fluorine two different ways. So we're going to take the iron plus 2, and then we're going to take the fluorine minus 1, and then we've got this one that we're going to say is a plus 3, and this one is a minus 1. So what's the difference between the plus 2 and plus 3? What's the difference between those two?
Charge.
Yep. So what did the iron plus 2 do to get its charge? Lost 2. And what did happen to the iron?
Lost 3.
Lost 3. These are elements off the middle of the periodic table. And some of these metals off the middle of the periodic table, they tend to have multiple ways in which they can lose electrons. Some of them choose to lose a certain number of electrons more often than the other case. So the one that's more common here, that we see most often, is the one that is plus 3. So the iron that's a plus 3 we see more often than the one that's a plus 2. Okay, so if you guys have your periodic table, you're going to have two values above that middle group. If you look at iron, it can be a plus 2 or a plus 3. Okay, so if it's a plus 2, we need two fluorines. So we need two fluorines. So that formula would be FeF2. Okay, if we have this one, we need 3 fluorines surrounding 1 iron. So there'll be 3 fluorines surrounding the 1 iron. So that's FeF3. So if we weren't thinking, we would say those would be both iron fluoride. But how do we differentiate between them? Because they're two different compounds with different properties. So how do you differentiate between these two irons? What do you have to use? Well, you could maybe do something to the ending, but that usually the ending goes with the second one, and the second one's the same on all of them. So really probably wouldn't be, you'd have to differentiate the first one somehow, that iron, that first one, to tell the difference between them. So how would you do it?
Would you want to put their charge?
Okay, you would put their charge. Doesn't that make sense?
Mm-hmm.
When you name them, you just represent their charge somehow. And you guys remember how we represent the charge, right? So we put down iron, and what do we put for iron's charge? Roman numeral 2. You guys remember that?
Yeah.
Okay, so that'd be iron 2 fluoride. So we have to differentiate between the two. So now, if you remember in the past, a lot of students thought that 2 represented how many irons we have. But now I hope you realize all we're doing is we're naming the iron based upon its charge. So this second one we'll say iron free. So the ones we have to differentiate between are the middle ones on this chart. So if you look at the middle ones on that chart, you realize that they have numbers up above there that are multiple positive numbers. Like manganese has how many different ways in which you have to identify the manganese?
5.
5 different ways. There's 5 different ways it can form a charge. Okay, how about cadmium? How many different ways does it form a charge? CD.
1.
Just 1. Do we have to write a Roman numeral for it? No, because we don't have to differentiate it from another cadmium. It can only be one charge. Okay, how about silver? Do we have to explain the difference of silver? No. It can only be a +1. All right. What about platinum? PT. Do we have to write? Okay, we do. All right. So I hope that's informative. I mean, I took a little bit longer than probably I should have, but you have to differentiate the 2 irons from one another, and that's how they do it. There was another way in which they did it. Do you guys see the other way in which they differentiated in the past? Did they give you any information in the book about ways you can differentiate between iron and +2 and +3? We're not going to use it, but just in case. Do they have anything in there? Do they have a table that has some like different endings?
Do you mean like the I and 8 and
No. Well, that's for your polyatomic ions.
Okay.
And that's how we can differentiate the number of oxygens in there, because it's kind of neat that nitrate has 3 oxygens and nitrate has 1 less. So the ITE is always going to have one less oxygen than the ATE, which is kind of good if you had to remember. So on each one of these, you're going to write the symbols for the monoatomic ion or the polyatomic ion, and then you got to make sure that your subscripts represent how many you have of each one in which to get that charge to balance, like we did on our previous examples. For every 1 strontium, it's -1. So we need 2 of these chlorates, so that should be SR, then ClO3 with a 2 behind it. Okay? Because we need 2 -1s to match like I showed you prior. We have to put it in parentheses, because if we don't, it looks like ClO32. So if we've got multiple ones hooked together, we always got to show parentheses around polyatomic ions. That's kind of like they show them anyway on your chart, kind of that way. Ammonium is a +1, sulfate's a -2. So now I need 2 ammonium. So I'm going to put NH4, which is the top. This is the one that's hard to find because students don't recognize it when they first start using the chart. And it's the one in the upper left. It's the only one that's positive on the chart, polyatomic ion table. So we need 2 of those for every 1 SO4. Aluminum oxide. Well, that I tells me it's off the periodic table and it's oxygen. And when I look up oxygen on the periodic table, when it becomes a -2 charge, that's the one I'm going to use. So you look at the end of the oxygen on the chart, and they only give you 1. They only say it's -2. And then you look at aluminum. Aluminum is a +3. So that's the one we need 2 aluminums for every 3 oxygens. So that's going to be Al2O3. Sodium is a +1. Carbonate is a -2 column, CO3. So that's why that one's Na2CO3. Now in that one, since I only have one CO3, I don't have to put it in parentheses. And then this last one, I don't even have to look iron's charge up because it's indicating the 3 is the charge. And oxalate's a -2. So that, again, we just need 2 irons for every 3 oxalates. Oxalate C2O4 with a 3 behind it. So these get very repetitive. 2 and the 3, what do you do? Well, you got to get 3 of the 2 and 2 of the 3 to get them to balance out. So I'll let you work on those last 5, 6 through 10, and see what you come up with for names. So just finish that up. The first one is what we call a binary ionic. This is where I said we got categories. So the first one's called a binary ionic. But you know the I by itself, and so it's off the periodic table. And that would not be iodine, but iodide. So the first one, we would name it as calcium iodide. Okay? The second one is what we call a compound that's a polyatomic ion compound, because it has a polyatomic ion in it. So that is a really easy to name as well. So that one would be aluminum nitrate. The third one, nickel, we looked that up, and it can be a 2 or a 3. So if you look above the metal and you see, now calcium we didn't have to do that for because it only had a +2 above it. So I didn't have to say it's calcium 2 because we don't have to differentiate it between anything else. This nickel we have to differentiate between. So we have to look at the charge of chlorine, and its overall charge overall is a -3. So which nickel do we have to show that? So what's the charge of nickel? +3, right? So that's why we have to say that's nickel-free chloride, because we have to explain what charge ion it is. Potassium we don't, so we just write potassium, and then BrO3 is bromate. Be careful because you could have bromate, bromite, hypobromite, or perbromate. Same with chlorate. You could have chlorate, chlorite, hypochlorite, perchlorate. So just if you have 3 oxygens, it's 8. And then the last one, it's NH4, so it's ammonium. And then it's oxalate. And that's it. So just the ones you have to be really concerned with that's going to give you issues is these ones that have Roman numerals. And so you just have to, if you realize that there's 2 charges to pick from, you have to find out what charge it is and use that as your Roman numeral, okay, when you do it. All right, I'm going to go ahead. So again, you're going to do page 67. You can do 75 ABEF, 76 ABEF, 79 and 80, all of them, which are just 4 each, and 83 A through D, which would be 4.